Hello, we are the Goofy Gophers, and today we are going to present the Muscular Hydrostat Snake Spine Inspired Gripper. Our group members are Bethany Calvert, Sam Glasgotter, Zach Majors, Isaac Martinez, and Matt McGraw.
For our discovery decomp, the hypothesis was that a snake backbone structure combined with the principles of a muscular hydrostats would make for a robust and flexible limb. With that in mind, vertebrae were designed with pilot holes for wires and a middle pilot hole for elastic bands to run through. They wanted to test the robot's motion dependent on which wires driven or pulled, how much power is consumed for different robotic motions, the comparison between the physical and model end trajectories, as well as the positioning error of the distal end. They observed how the robot's motion changed as different sections were pulled, and found that pulling different sections together or separately caused different forms of motion in the arm. They measured the power consumption for different sections pulled and different applied bending moments, and found larger bending moments and pulling cables at the same time caused higher power consumption. They measured trajectories of the distal end using grid paper and compared it with model predictions, and found that the trajectories matched reasonably well. And they measured the relative position error based on what the actual distal end position was supposed to be, and found the positioning accuracy of the wire-driven arm was actually fairly low. Upon testing the hypothesis, it can be seen that the wire-driven system is in fact robust and flexible, but power consumption could be minimized, and the end position accuracy could be improved using a feedback control system.
The first animal that we chose to take inspiration from was a snake. Snakes have flexible backbones with repeated joint structures, and we use this in our design by using 7 identical vertebrae or joint structures, and each of these vertebrae employ about 14 degrees of freedom in one plane, similarly to how a snake employs 10 to 20 degrees of freedom in one plane. And overall, just like a snake, our fingers have a very large curvature of their entire trajectory because of the rotation in each vertebrae. Likewise to a snake, our gripper also depends on an increased contact area. The vertebrae form around the object that they are grasping, and it allows for a more robust connection to the gripper's object.
The other animal we took inspiration from is the octopus, due to their tentacles functioning as hydrostats, meaning that they maintain a constant volume during actuation. They have 8 arms composed of muscular arrays consisting of longitudinal, transverse, oblique muscles with no skeletal structure. This allows them to have virtually unlimited degrees of freedom. During motion, the cross-sections and lengths of the tentacles contort, but we didn't utilize this feature in our design. Mostly, we just adopted the mechanisms used for bending based on their antagonistic longitudinal and transverse muscle interactions, and we mimicked this using rubber bands and fishing line in one plane only. Due to time constraints, we have not implemented nearly as complex muscular arrays that we could have to increase their degrees of freedom substantially.
For our design, we knew that we wanted to incorporate the repeated joint structure of a snake skeleton, as well as the muscular hydrostat structure from octopus tentacles in order to achieve bending actuation. Our gripper will make use of a maximum contact area in order to increase the efficiency and be able to grab oddly shaped objects. Our gripper will also constrain motion for each of the fingers to a curve in a 2D plane, as well as having 3 individually controlled fingers with 1 degree of freedom each, totaling to 3 degrees of freedom.
Our fully assembled design includes a gripper that has 3 fingers, each with 7 cylindrical joints, and then 1 circular fingertip. Each of the fingers has 3 muscle structures, a fishing line that allows for the actuation of each finger, as well as 2 rubber bands that returns each finger to its resting position. Each finger is driven by a separate servo that pulls on the fishing line to allow for the actuation. You can see that our design allows for us to pick up fairly simple objects, such as this perfectly spherical foam ball, as well as more complicated objects, such as this small little screwdriver right here. And there it goes. If we were to make future adaptations of this design, we would attach material to the fingertips for better grip on smooth objects. We would increase the degrees of freedom on each finger, probably by drilling more pilot holes and allowing for the finger to go not just this way, but in a couple different directions as well. We would probably increase the number of joint segments and fingers and just the overall size of everything. And we would also improve the actuation control with some stronger servos, because we were noticing we weren't getting as strong of grip force as we maybe would have liked.
These videos display how the gripper takes the shape of the object. You can notice that the fingers are straight in that video, and here it curves around the mouse. Here we show that the gripper still works despite joint failure at lower joints. And lastly, our gripper can feed people cookies. How cool is that?